Hey guys, welcome back. We're jumping right back into Chapter 7, and this section of the lecture we're going to cover precipitation reactions, and we just talked about in our Zoom meeting how understanding the importance of solubility when it comes to precipitation reactions. And so here's just a quick fun fact. So laundry detergent works better than soap because it contains substances that soften hard water. So what does that mean? Hard water, first of all, is the presence of magnesium and calcium ions. So if you have sodium carbonate, right, in laundry detergent, it reacts with actually these dissolved ions to form solids that basically precipitate from solution. That means they crash out, or they were in solution, they were soluble, but then they form a solid, and if you want to think about it like falling to the bottom of the beaker. So solids essentially fall out of solution. These reactions are examples of precipitation reactions, and again, a precipitation reaction forms a solid called a precipitate upon mixing two aqueous solutions together. The key to predicting precipitation reactions is understanding that only insoluble compounds form precipitates, so that is why it's important to know how to read that solubility table. So in these reactions, two solutions containing soluble compounds combine and an insoluble product is formed, and that insoluble product precipitates out of solution. You will need to know how to read the solubility chart. Again, this is the solubility chart right here, and we will look at this a lot throughout this lab, or this lecture. Okay, that flipped around. Okay, so because this is pretty important, but this is the way that I like to write precipitation reactions is a little bit different than how the book describes it. It's essentially the same thing, but this is just a little bit of a different method. So go with which one you like best. I think in these slides I have both, so you can look at both. So the first step is you're going to begin by writing the reactants, including the phases. All right, you don't write the entire skeleton reaction, so you read the paragraph, right, the word problem, and what you want to do is pick out the reactants, and you want to write out the reactants, and you want to include the phases. And just really fast, you'll need to have a firm understanding of nomenclature, meaning the naming of compounds, from Chapter 5 in order to write out the reactants. But you need to include the phases, okay? If each reactant is aqueous, then break that reactant up into its respective cation, and anion directly underneath. The cation, so say you have two salts and they're aqueous, so you break them up, so you're going to have two cations and two anions. The cation from one compound can now pair with the anion from the other compound to form, that should say, a new and potentially insoluble product. Charges must balance, so you may need to adjust the coefficients of each ion. I'll show you how to do that in a second. So once you figure out what the products that are being formed, you're going to write the new compounds on the right side, on the product side of the equation. So you're going to go back up and finish your skeleton equation. But because you broke up the cations and anions first, and you balanced the charges with coefficients, you shouldn't have to go back and rebalance the whole equation. Again, I'll show you how to do this in a second. And then finally, once you have a balanced chemical equation, with all appropriate reactants and products, then you're going to consult your solubility table to determine the phases. If the products are both soluble, then no reaction occurs. If one or both of the products are insoluble, a precipitation reaction occurs. So let's go through this. All right. So I don't have I already wrote the skeleton equation for you, or the beginning parts of the skeleton equation for you, so you don't really have to worry about that. But sometimes you'll have to read, like I said, a paragraph, and you'll have to pull that out, all right? So we have 2 moles of potassium iodide react with 1 mole of lead nitrate to form what? Now they're both aqueous. So what you want to do is jump down. So we already wrote begin by writing the reactants, including the phases. We already did that right here. All right. I did that for you. So if each reactant is aqueous, which they both are, then you can break them up into cation and anion directly underneath. So I'm going to do that right now. So I'm going to write 2K plus, comma, 2I minus. Now I do the commas because I think your book does always plus, 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 but I do the commas because I like to keep track of the fact that originally these two were part of the first reactant, okay? And then we have lead, Pb. Now lead is a 2 plus, and we know it's a 2 plus because we have 2 nitrate anions that are both 1 minus. Okay, so now that we have everybody broken up, we know that even though they're broken up, this was a part of the original compound, and then these two were the original compound. Then what we can do is we can essentially swap partners. Where potassium was originally bound to this iodide, now it's going to go over and it's going to be bound to this nitrate. And it looks like there's 2 and 2, so we don't really need to do anything, right? We don't need to do any balancing like that. So I'm going to go back up to here, and I'm going to write 2KNO3, and I'm going to leave my phases open because I'm going to evaluate that later on. Now we're going to swap the cation and anion from the original 2 compounds. So we have lead and iodide. Lead is a 2 plus, right? And it looks like we have 2 iodides right here, so that's already balanced. Now if it wasn't balanced, we would have to write a 2 here and do that, all right? But it turns out it's already balanced. So that's going to go, it's going to be, here I should do it like this. All right, so we're finished, almost. Everything's balanced, it looks great, but what we have to go in and do now, we have to fill out this right here. So I consult my solubility table, and long story short, all nitrates are soluble, so I'm going to write an AQ. And it turns out that lead nitrate, spoiler alert, is not soluble. And again, I just know this because I've done this, I've lectured on this before. But if you just look at your solubility table, we have lead iodide. Iodide is soluble. Compounds containing iodide are soluble, but if we look over at our exceptions, you'll see that lead is an exception. Compound is insoluble. So, because that's the case, then we have an insoluble product right here. Now, because this is insoluble, that means these 2 aqueous solutions were mixed together, and this solid crashed out, it precipitated out, and because it formed a solid from 2 aqueous solutions, this is, in fact, a precipitation reaction, okay? Right here, right, because of this. So let's take a look at what's going on. So again, we have potassium iodide and we have lead nitrate, all right, and they're both aqueous solutions. So basically this means that they're both mixed with water, they're in 2 separate beakers, right, and because they're aqueous, these cations and anions, right, the bonds, the ionic bonds break up when they are put into solution, and the cations and anions are dissolved and they dissociate completely and they move freely within the solution, okay? So because both of these guys are soluble in water, they dissociate completely and we have these 2 aqueous solutions. Now, the instant that the solutions are mixed together, all 4 ions are present in water, all right? this allows everybody to interact with each other. And it turns out, so remember, potassium was originally bound to iodide and it dissolved in water. But now we have iodide right here interacting with lead. And we found out, what did we find out? We found out that lead iodide was insoluble in water. So when these two interact, the forces, the attraction forces between them are greater than the attraction forces between the solvent, right? They quickly come together and they form a solid, and essentially sometimes it'll float, depends on the density of the solid. If it's more dense than water, it will sink to the bottom. If it's less dense than water, it will float to the top. But either way, a solid crashed out. These are now no longer all the lead and iodide ions come together, form a solid, and crash out, and that's where this comes from right here, this lead iodide solid part. So this is a precipitation reaction, okay, and you can see it right here. We have a beaker that was filled originally with lead nitrate, and then we have another beaker with a pipette that was filled with potassium iodide. Both were aqueous solutions. Then we mix them together, and as soon as we mix them together, the lead that's originally dissociated, reacts with the iodide that was dissociated in the first solution, and this bright yellow precipitate forms, and that is the lead iodide. That's the solid lead iodide. So let's do another example. Write an equation for the precipitation reaction that occurs when solutions of sodium carbonate, now I gave you sodium carbonate, and copper chloride are mixed. Sometimes I won't give you that. Sometimes I won't give you the sodium carbonate, right? You're just going to have to remember what sodium carbonate is. But in this case I did. So we have, and they're both aqueous, so we have sodium carbonate AQ plus, and we have copper chloride AQ. Now, the first thing that you want to do, I like to break the reactants up into cations and anions. So I'm going to do that right now. So we have 2Na plus, comma. Now I put the 2. I put the 2 here because, right? So I'm showing that there are 2 sodium cations when that dissociates in water, and for every 1 carbonate anion plus. Now, what's the charge on copper for this guy? Because we have 2 chloride anions, we're going to have copper 2. So it's going to be Cu2 plus and 2Cl minus. Again, this 2 came from the fact that there are 2 chloride anions in this solution right here. All right. Now what we're going to do is we're going to pair up the cation from the first reactant to the anion of the second reactant. So this is the cation from the first reactant, and that is going to pair up with the anion from the second reactant right here. And it turns out, luckily, right, that these 2 are balanced. Okay, 2 and 2. So we're going to go back and, sorry, just a second. We're going to go, oh, I messed something up really fast. I'll fix this. There we go. All right, so we don't have to do any balancing because everything's already balanced. The coefficients are there. It's all good. The charges cancel out. So we're going to write 2NaCl. I'm going to, right, because I don't know what the phase is, and then I say plus, and now the cation from the second is going to pair up with the anion from the first, and again, copper 2, carbonate, those guys cancel out just fine, the charges cancel, so I'm going to write CuCO3. All right. Now what I have, and I don't have to finish this part just yet, right? I don't have to, this is something else that we'll talk about later. But I wanted you to get in the habit of writing this out so you could see what's going on, okay? So now we have to consult our solubility table, all right, and to see what's going on. Sodium chloride is always soluble, so I am going to write AQ here, but the big question is, how is this copper carbonate? So let's go back to my solubility table, copper carbonate. So for copper carbonate, we're looking at carbonate. Here's carbonate, and we're going to, so it's probably going to be insoluble unless that we see a copper exception, which we don't. So it looks like it is insoluble, so I'm going to go back down. And I'm going to write an S for solid. All right? So this is a precipitation reaction, and it's a precipitation reaction because it makes this copper carbonate. When we mix two aqueous solutions, we end up getting out copper carbonate as a solid. All right, let's do one more. Well, we're going to do a lot more. Write an equation for the reaction that occurs, if any, when solutions of sodium carbonate and, oh, we just did that one, didn't we? Oh, I know what I did here. I'm sorry. So I wrote this out for you guys so you could see. We can forget that. Okay, because we just did it, right? We can move on. All right, let's try another one. Potassium iodide and sodium chloride. So again, they're both aqueous, so we can break them up, and we're going to say K plus, comma, I minus, plus Na plus, comma, Cl minus. Okay, now we're going to pair this guy up with, this guy. So we're going to make potassium chloride, and we're going to make iodide and sodium come together. All right, so we have all the charges are good. So that's how quickly you can do it. All right, because all the charges cancel. So that's great. Now we can solve our solubility table. Long story short, everything is insoluble, or everything is soluble. Potassium chloride is soluble in water, and sodium iodide is soluble in water. And since these two are both soluble in water, we would say overall no reaction. All right? No reaction, no overall reaction, no precipitation reaction. We did not form any solids. And why is it a no reaction? Well, here's why. If we were to take aqueous potassium iodide and pour it into aqueous sodium chloride, everything still stays in solution. Everything is still dissociated. Nothing crashes out. There's no change. There's no overall change from reactants to products. And because there's no change at all, we say that no reaction occurs. Okay? We say that no reaction occurs. So in precipitation reactions, when you see something like this, when you have aqueous, you add them together and you still get aqueous and aqueous, then we say overall no reaction occurs. And we will dive into this a little bit more deeply later on in this lecture. Okay, so now I want to introduce to you, so now that we know how to write out precipitation reactions and we know what those mean, I'm going to introduce, that's what we did, what we had been doing is we had been writing the molecular equation, all right? We've been writing the molecular equation. That's what I've taught you how to do so far. But now I'm going to introduce to you a complete ionic equation, all right? So first, let's do this, all right? Let's write the molecular equation for aqueous silver 1 nitrate that reacts with aqueous sodium chloride, all right? So we're going to do the molecular equation, and we're going to say aqueous silver 1 nitrate, so it's aqueous silver 1, so Ag nitrate, NO3, AQ, reacts with aqueous sodium chloride, to form what? All right. So remember what I told you originally, what I like for you guys to do is I like for you to break these guys up if they're aqueous. And I still want you to do that, but turns out that is actually the first step in writing a complete ionic equation. So just bear with me. So Ag plus, comma, NO3 minus plus Na plus, comma, Cl minus. All right. Now what you went ahead, what this is, even though I told you to do this, originally, this is actually, again, the first step in writing a complete ionic equation. All right. I will do it for you first, and then I'll explain to you what it is. All right, so now that we wrote this out, what we're going to do is we're going to combine everything and finish this portion. All right, we're going to finish the molecular equation right here. So we're going to sit back and say silver right here comes together with chlorine, all right, to form AgCl, all right, plus, and again, sodium and the nitrate come together. So, and it's a 1-to-1, everything's fine. So we have sodium, NO3, AQ. All right, we have not finished the molecular equation yet. We need to find out what's going on here in terms of solubility. Consult my solubility table. Sodium nitrate is aqueous, but silver chloride is not. It's solid. Okay. So again, we just completed the molecular equation, which is an equation showing the complete neutral formulas for every compound in the reaction. Now that we've finished the molecular equation, we can go back and finish the complete ionic equation. When I finish this, that will essentially tell you or show you what a complete ionic equation is. So it's the same thought process, all right? On this side, down here, that it is this side going down here. We were able to break these up into cation and anion because these guys were aqueous. Now we're going to do the same thing here. The only difference is this guy is a solid. And since this is a solid, we know that if we drop it in water, it doesn't dissociate, so we can't break it up. We have to bring it down. And this sodium nitrate, because it's aqueous, we can break that up. Na plus, comma, NO3 minus. Go ahead. Now this right here is a complete ionic equation. All right. This shows aqueous ionic compounds that normally dissociate in water or in solution as they are actually present in the solution. So in this solution, when we pour this and this together, we end up forming this, and then this is still dissociated. Okay? So long story short, you're going to break everything up into ions if they are aqueous. If they're not, like this silver chloride, when you bring it down to write the complete ion equation, you have to keep this together because it doesn't break up in solution. So when writing complete ionic equations, separate only aqueous ionic compounds and their constituent ions. Do not separate solid, liquid, or gaseous compounds, okay? It's only going to be the aqueous ionic compounds, okay? So this is another example. This is from your book. This is a complete ionic equation, right? This is the same thing that I wrote here. The only difference is it's stylistically a little bit different. All right, let me actually cut this and move this flip down so you can see it better. So again, stylistically, it's a little bit different. The only difference is between what I wrote and what your book has is your book includes the phases, right, down here, after every single ion. I don't, because if I have it as an ion, I'm saying it's aqueous. That's okay for me. Just a heads up, your lecture instructors in the future might not like it like that. They might want you to write AQ after every single ion, so just a heads up on that one. And the other difference is that I have a comma in between my original cation and anion. Your book doesn't. It adds a plus. Again, this is just a stylistic thing. I like to keep the comma there because it just keeps, like, this broke up into that. So I like to keep these guys kind of associated. Again, your book doesn't do that. It just does plus, plus, plus. So keep that in mind. Sorry, I'm going to take a quick drink of water. Hold on. And I'm really sorry if that was really loud. But what are you going to do? Okay, so now that we know about complete ionic equations, I can introduce this term spectator ion to you, all right? Spectator ions are ions that appear in here. Okay, they are ions that appear in the reactants as well as the products. And you'll see here that your this image that I have, the spectator ions are very clear, right? NO3 is a spectator, is an ion on the reactant side, and then if we the reactant side, if we go to the product side, turns out it's still over here, so this is called a spectator ion. Same with the sodium. What is not a spectator ion is our silver ion, our chloride anion, and then the compound that's formed. All right, so when we take out spectator ions, this, I'm kind of jumping ahead, but it's fine. But when we take out these spectator ions, right, that gives us a net, ionic equation. All right. So let's move a little bit forward. So writing, okay, complete ionic, okay, and this is net ionic. So to simplify the equation and more clearly show what is happening, spectator ions can be emitted or canceled out. Equations such as this one, which show only the species that actually participate in the reaction, are called net ionic equations, right? So what I did is I canceled out this is, remember, so this is the molecular equation right here. This and this is the total ionic equation, and then when you remove the spectator ions, right, you are left with a net ionic equation, right, that removes all the spectator ions. Sorry, I feel like this is the same. Yeah, I don't know why this is double. Okay, so now that we have three types, molecular, complete, and net, we can write a molecular, complete, and net ionic for this precipitation reaction. All right, silver 1 nitrate and sodium carbonate. So let's get started. All right, so first I'm going to write silver 1 nitrate. So I have AgNO3, and it is aqueous. Consult my solubility table. Plus sodium carbonate, Na2, because sodium is always a +1 cation, carbonate is a -2, sodium 1 carbonate, and that is also aqueous, all right? And that goes to, we don't know just yet, all right? I'm starting my molecular, but I'm not finishing it, and I'm going to jump down to make a complete ionic, a complete ionic really fast. Because when I do the complete ionic, the reactant part of the complete ionic, it helps me complete the molecular. So here's what I mean. So I'm going to break these guys up, Ag plus, comma, NO3 minus, plus, again, I'm able to break these up because they're all aqueous, Na plus, plus CO3 2 minus. Now I'm going to take the cation from the original, let's do it like this, and I'm going to pair that up with the anion from the second compound. Now here's the deal. This is actually really important. You'll notice that silver is a +1 and carbonate is a -2. I can't put these together just like this because the charges don't cancel. So I'm going to need 2 silvers for every 1 carbonate. So I'm going to put a 2 right here. Since I put a 2 right here, I have to go back up and put a 2 up here. And since I put a 2 up here, that means there are 2 nitrates. So I'm going to have to put a 2, move this over, right here. All right, this is why I start the complete ionic first without finishing the molecular, for this reason, all right? Because this allows me to balance much, much, much easier. So now that I have it together, now I can go ahead and finish my, start to finish my molecular. So I have Ag, silver, subscript 2, CO3, I don't know what the phase is, and now, and look at this, I take my sodium cation and I'm going to pair that up with nitrate, right? And now, because I put the 2 right here for nitrate, now this is automatic. These are automatically balanced. Oops, I forgot to put the minus sign. All right, so that's going to form 2 sodium nitrate. And I'm going to put an AQ here because all nitrate molecules or salts are soluble. So the question is this guy soluble? And turns out this guy is not. If we consult the solubility table, carbonates aren't usually soluble. Definitely silver carbonates are not. So I'm going to put a solid S right there. Now that I have the phases, everything's balanced, right, for my net ion or molecular. And now that I have the phases, I can go back down and complete my total. So I'm going to say, now, because this guy right here is a solid, I cannot break him up when I bring him down. I have to keep them together. So Ag2CO3, solid, plus, and since this is aqueous, I have to break it up. 2Na plus, comma, 2NO3 minus. Now again, I have the 2 here because there are 2 sodiums and 2 nitrates. All right, so I just did a molecular and a complete ionic equation. Everything's balanced. Now what I'm going to go and do is I'm going to finish it off. Oops. That's annoying. Here, let me try this again. Let's see. Oh well, I'll just fix it. Alright. Now what I'm going to go ahead and do is I'm going to identify the spectator ions, take that out, and I'll have a net ionic afterwards. So silver, I'll start from the left. I have a silver nitrate ion here, and I don't have any over here on the product side. So looks like I'm keeping this, okay? Nitrate, 2NO3 I have right here, and look, I have 2NO3 on the product side, so I'm going to do this. Actually, this might be easier. Do that. That's a no, and that's a no, and I'm going to delete that because I'm going to keep it. Next one, sodium. I have a sodium, 2 sodium cations here, and look, I have 2 sodium cations here, so I'm going to mark these guys out. And then I have a carbonate and no carbonate, right? And then on this side, I have nothing over here. So I'm going to take him, him, and him, and I'm going to bring it down. So it's going to be 2Ag plus CO3 2 minus goes to Ag2CO3. Solid. All right. And again, I'm not writing aqueous after every single one, just because it's time consuming, right? But you need to have phases in you definitely, whatever you do, you need to have phases in your molecular, all right? So again, this is my molecular, this is my total or complete ionic, and then this is the net ionic. All right, let's do another one, and then we're finished. Okay, so we need to do the same thing for the reaction between ammonium nitrate and potassium chloride. So ammonium nitrate, NH4NO3. That's aqueous. I know it is because it's a nitrate, and all nitrates are aqueous. Plus potassium chloride, and that's going to be Ki aqueous. All right, before I do my, before I finish my molecular, I'm going to begin the complete ionic. All right, by breaking everything up. So NH4 plus, comma, NO3 minus, plus K plus, plus I minus. Again, I can break these up because they're all soluble. They're all aqueous solutions. Oops, sorry about that. Now that I have started my complete ionic, I'm actually not going to finish it until I finish the molecular, all right? And I'm going to finish it by making sure that everything balances out. All right, everything's 1-to-1, so I don't really need to do anything. I know that this ammonium, right, is going to pair up with iodide, so it's going to be NH4I. I don't know what the phase is, plus, and potassium nitrate, KNO3, and, oops, I'm trying to zoom in, it's not working, AQ. Sorry, that's ugly. All right, so ammonium, we need to figure out, big question, again, nitrates are all soluble. The big question is this soluble? So we're going to go, here, I'll do this. And again, we are looking at, sorry, just everybody close your eyes, this might make you dizzy. we're looking at ammonium nitrate, or ammonium iodide. And we're going to go back up to our solubility table, and we're going to sit back and say, okay, ammonium right up here. Are there any exceptions? None. And anyway, iodide, it's also soluble too. So let's go back. Looks like it's soluble. So I'm going to go back here, and I'm going to write AQ. Okay, so this looks like a reaction that doesn't happen, or we would normally write no reaction here because look, aqueous and aqueous. So let's take a look why. So we're going to finish our complete ionic by breaking everything up. NH4 plus I minus plus K plus comma NO3 minus, because everything's aqueous. Now we're going to go in and we're going to do our net. And we're going to do our net by removing all of the spectator ions, okay? So NH4, right? That's here, and look, NH4, so it looks like that's gone. NO3, NO3, both gone. K plus, gone. And I minus, gone. So there's no net reaction. There is actually no reaction to begin with, and that is because in order to have a reaction, you need to have the products need to look different than the reactants. And you might sit back and say, oh, but it is different. Look, because here NH4 is with iodine, and over here NH4 is with nitrate. But because everything is aqueous, when we throw it all together in solution, everything dissociates and nothing crashes out. So the whole thing is spectator ions. Nothing happens. There's no difference between the before and the after. There's no difference between the reactants and the products. So because of that, we have no net reaction, no overall reaction, no net ionic and no overall. Okay, so to summarize, so just really fast, that is why when we went back up to that is why if we have aqueous in the product side, we have no net reaction. So, all right, I'm going to wrap this up just by summarizing. A molecular equation, which we learned, is a chemical equation showing the complete neutral forms for every compound in the reaction. A complete ionic equation is a chemical equation showing all of the species as they are present in solution. And a net ionic equation is an equation showing only the species that actually participate in the reaction. Right? So that is, we're going to go ahead and stop precipitation reactions, and when we pick back up, we're going to talk about acid-base reactions. So stay tuned.